In this lecture, we are looking at the performance measures for a discrete control system. We shall begin with a review of the mapping of points from the S-plane into the Z-plane. Let's look at the mapping of the primary strip from the S-plane to the Z-plane. The imaginary axis of the S-plane maps into a unit circle in the Z-plane. The left-hand half of the S-plane maps into the interior of the Z-plane unit circle. The right-hand half of the S-plane maps into the exterior of the Z-plane unit circle. For a point in the S-plane with a real part equal to sigma, the corresponding point in the Z-plane has a magnitude equal to e to the sigma t. This means that all points in the S-plane with a real part equal to sigma will map into a circle of radius e to the sigma t in the Z-plane. In the illustration, we have two sets of points in the S-plane with respective real parts sigma 1 and sigma 2. When they are mapped into the Z-plane, they map into respective circles of radius e to the sigma 1 t and e to the sigma 2 t. For a point in the S-plane with an imaginary part equal to j omega, the corresponding point in the Z-plane has an argument equal to omega t. This means that all points in the S-plane that have an imaginary part equal to j omega will map into a straight line that makes an angle omega t to the real axis of the Z-plane. In the illustration, we have three sets of points that have respective imaginary parts j omega 1, j omega 2, and minus j omega 3. When these points are mapped into the Z-plane, they will map into straight lines that make respective angles omega 1t, omega 2t, and omega 3t to the real axis. Let's look at points that are commonly found as poles. Real negative pole. In the S-plane, the point is described by s equals minus a. When mapped into the Z-plane, the corresponding point has a magnitude equal to e to the minus at. Pair of complex conjugate poles. In the S-plane, the points are described by s equals zeta omega n plus or minus j omega d. Zeta is the damping ratio, omega n is the natural frequency, omega d is the damped frequency. When mapped into the Z-plane, the magnitude is e to the minus zeta omega n t. The arguments are plus or minus omega dt, which can be expressed as plus or minus 2 pi omega d over omega s. Omega s is the sampling frequency and is equal to 2 pi over t. So to get the expression 2 pi omega d over omega s, we substitute for t in omega dt. In transient performance analysis, we are interested in response time, overshoot, and settling time specifications of a control system. In discrete control systems, these specifications place constraints on the damping ratio, natural frequency, and sampling frequency. Therefore, in the design of control systems, we select values for the damping ratio, natural frequency, and sampling frequency to meet the required transient performance criteria. Let's look at the conditions for meeting a specified settling time. The 2% settling time, Ts, is equal to 4 over zeta omega n. That is, zeta omega n equals 4 over Ts. We observe that zeta omega n is the real part of the poles of the system. Therefore, to meet a specified settling time, the real part of dominant poles must be equal to 4 over Ts. When we map these points into the z-plane, they map into points with a magnitude equal to e to the minus 40 over Ts. This means that for a given settling time Ts, the poles must lie on a circle of radius e to the minus 40 over Ts in the z-plane. That's the illustration there. In the S-plane, the points that meet a given settling time will lie on a vertical line that passes through the point 4 over Ts on the real axis. When they are mapped into the Z-plane, they will lie on a circle with radius of e to the minus 40 over Ts. Let's go into the conditions for meeting a specified damped frequency. Damped frequency omega d is the imaginary part of a pole in the S-plane. Now, the imaginary part of a pole gives the argument of the corresponding point in the Z-plane. Therefore, for a given damped frequency, poles lie on a straight line that makes an angle omega dt with the real axis in the Z-plane. Thus, the illustration: in the S-plane, points that meet a specified damped frequency omega d lie on a horizontal line that passes through the point omega d on the imaginary axis. When mapped into the Z-plane, the points will lie on a line that makes an angle omega dt with the real axis. Specifications that place a constraint on damped frequency omega d imply that the Z-plane poles must lie on a line that makes an angle omega dt with the real axis. As an example, specified peak time Tp1 is equal to pi over omega d. This means that omega d is equal to pi over Tp1. Therefore, the argument of the poles that meet this specification is equal to pi t over Tp1. Hence, the poles that meet this specification must lie on a line that makes an angle pi t over Tp1 with the real axis of the Z-plane. For a specified damping ratio, the poles must lie on a logarithmic spiral in the Z-plane. A performance specification, which implies a certain damping ratio value, requires the Z-plane poles to lie on the spiral. An example of a specification that constrains damping ratio is maximum overshoot. Thus, an illustration: in the S-plane, points that have a constant damping ratio lie on a line that makes an angle phi with the negative real axis. The angle phi is equal to the inverse cosine of the damping ratio. When the points are mapped into the Z-plane, they map into a spiral. Let's look at the conditions for meeting a specified sampling frequency. Sampling frequency is usually specified as a multiple of damped frequency, that is, omega s equals n omega d, where n is the multiple. This means that omega d equals omega s over n. The argument of the corresponding point in the z-plane is omega dt. If we substitute for omega d using omega s over n and t using 2 pi over omega s, we obtain the argument as 2 pi over n. Therefore, for a specified sampling frequency, the corresponding z-plane pose must lie on a line that makes an angle 2 pi over n with the real axis of the z-plane. Thus, an illustration for the positions of the poles required to meet a specified sampling frequency. The loci for the respective different conditions described to this end may be placed on the same z-plane. From performance specification constraints, we can then derive the regions in which the poles should lie to meet given performance specifications. Therefore, these combined loci can be used as a design tool for the design of control systems. Steady-state error. From an earlier derivation, the error Ez is equal to Rz over 1 plus dz gz. The steady-state error is the value of the error when time goes to infinity. Using the final value theorem, the steady-state error is equal to the limit as z goes to 1 of 1 minus z to the minus 1 by Rz over 1 plus dz gz. Position error constant. Let's consider the case when the input is a unit step input. If we substitute for the input in the expression for the steady-state error, we obtain the steady-state error as being equal to 1 over 1 plus the limit as z goes to 1 of dz gz. Now, let's define the limit as z goes to 1 of dz gz as being equal to the position error constant Kp. This means that the steady-state error is equal to 1 over 1 plus Kp. Therefore, for a zero steady-state error for a step input, Kp must be equal to infinity. This implies that dz gz must have at least one pole at z equals to 1. This pole is the one that will force Kp to go to infinity. Velocity error constant. Let's consider the case when the input is a unit ramp input. If we substitute the input into the expression for the steady-state error, we obtain the steady-state error as being equal to t over the limit as z goes to 1 of z minus 1 by dz gz. Let's define the velocity error constant Kv as being equal to the limit as z goes to 1 of z minus 1 dz gz over t. Then the steady-state error for a unit ramp is equal to 1 over Kv. This means that for a zero steady-state error for a ramp input, Kv must be equal to infinity. This implies that dz gz must have at least a double pole at z equals to 1. Acceleration error constant. Let's consider the case when the input is a unit parabolic input. If we substitute the input into the expression for the steady-state error, we obtain the steady-state error as being equal to the limit as z goes to 1 of t squared over z minus 1 squared dz gz. Let's define the acceleration error constant Ka as being equal to the limit as z goes to 1 of z minus 1 squared dz gz over t squared. Then the steady state error for a unit parabola is equal to 1 over Ka. This means that for a zero steady state error for a parabolic input, Ka must be equal to infinity. This implies that dz gz must have at least a triple pole at z equals to 1. I recommend that you do these questions from chapter 7 before you proceed to the next lecture.